Every day is full of decisions. From what you eat for breakfast to what you wear, decisions can be big or small, but altogether, they shape your life as you know it. On average, a person will make 35,000 decisions in a day. Conscious and unconsciously, your brain is working hard to make the decisions that are best for you. However, what if your brain was wrong? Different psychological tests have been designed to put the brain's decision-making skills to the test. One of these, the Iowa gambling task, taps into the brain's desire to balance risk and reward. To better understand the neural mysteries behind the decision-making in this task, a study set out to see what functional areas were associated with it, and to a greater extent, decision-making in general. Previous studies have already helped to pinpoint two main areas of interest in the brain, and those are the default mode and frontoparietal networks. The FPN plays a central role in cognitive control during task states, while the default mode network is most commonly active at rest, when awake, and when the brain isn't involved in any task. Specifically in the FPN, little research has been done to understand the changes in functional network organization across states in this area. However, multiple areas in this network have been implicated in the IGT, Iowa gambling task, specifically the DLPFC, has to do with making processes, and the ACC, particularly in the dorsal area. By better understanding the connectivity of these areas, we can better understand how the brain communicates and integrates the function of different areas to come to a conclusion. In the study we are going to delve into today, whole brain metrics were used, which means that the networks of the entire brain were analyzed. It was hypothesized that while at rest, the brain would function with smaller, more local networks, and while completing the IGT, the brain would communicate more globally to complete the task. The two areas of interest would also be examined more closely both within and between tasks, with the FPN expected to increase in functional significance. Data was collected from 9 young, healthy adults. Firstly, an anatomical brain scan was collected for each participant for 5 minutes, followed by participants alternating between a resting state, during which they looked at a fixated cross without moving for 4 minutes, followed by the IGT task for 4 minutes, and then followed by a spatial orientation block which was not included in analysis. This was repeated 4 times, and at the end of the experiment, a perfusion sequence was collected where the participants rested with their eyes closed for 5 minutes. A computerized version of the IGT was used. Participants indicated their selection from one of 4 decks, and after each response, a screen appeared displaying whether the response resulted in a win or loss, the win or loss amount, and their total earnings. Selections from decks 1 and 3 yielded a reward of $150, while the selections from decks 2 and 4 yielded a reward of $200. The loss amount also varied with each deck. Penalty amounts were higher in the high-paying decks and lowest in the low-paying decks. To compare the two networks, masks were created using software that placed 10mm spheres in regions of interest. These ROIs were then used to extract a network metric of interest for each voxel, which were then averaged to attain a mean value for each network. To establish the functional significance of connectivity metrics, a linear mixed model predicting IGT performance was used. Differences in the spatial distribution of hub nodes between REST and IGT was calculated using degree centrality, i.e. the number of connections per node. Hubs were identified as those nodes in the top 20% of that network. Comparisons between all networks across participants and tasks created a similarity matrix, and the average similarity within tasks was divided between tasks to generate a comparison statistic which is analogous to an ANOVA. Now on to the results. To begin, we will examine the participants' general performance on the Iowa gambling task. On average, the participants made more selections from the advantageous decks compared to the disadvantaged decks. The following graph indicates the average of all the participants' successful choices for each of the 4 blocks of IGT. A one-way repeated measures ANOVA showed no significant difference in success rates among each block. This indicates the participants did not improve on the Iowa gambling task over time, no learning effect. However, the fact that participants did on average select more cards from advantageous decks confirmed that the participants were well engaged in the task during the experiment.
Next, we examined whole brain metrics. It was found that there were no significant differences in REST or IGT across the 4 sessions, indicating that overall network activation during REST and IGT was the same across tasks. There were, however, significant main effects for both metrics between REST and IGT. Consistent with the original hypothesis, local efficiency decreased from REST to IGT, whereas global efficiency increased. The spatial consistency of the top 20% highest degree nodes were examined across REST and IGT. A permutation test was conducted, and it was found that there was significant difference in key nodes between REST and IGT. The degree of consistency images was used to examine where these changes occurred. Next, we turn to differences observed in the DMN and FPN from rest states to task states. Again, this was done using repeated measures ANOVA, examining degree, local efficiency, and global efficiency across all 4 sessions. These calculations were done for each region of interest, respectively. Once again, it was found that activation of the regions of interest did not change across sessions. The default mode network was found to significantly decrease in global efficiency from REST to IGT. Consistent with researchers' hypotheses, degree as well as global efficiency significantly increased from REST to IGT in the FPN. It was also found that degree, global efficiency, and local efficiency were significantly higher in the DMN compared to the FPN during REST, but there were no significant differences in these factors during IGT. A linear mix model was used to predict IGT performance from observed network metrics across both the FPN and the DMN. The results revealed that no metrics in either system were predictive of IGT performance. So those were the results, but how are they relevant, and how does this knowledge contribute to the field of psychology? Well, firstly, we know that the brain does shift in network connection from resting states to task states. So if we dive in more specifically, we know that during rest, the brain is in a more clustered and locally ordered topology. Whereas when it's in decision-making tasks, such as IGT, the brain shifts to a more diffuse and globally ordered topology. This may be because the brain is drawing on different networks in different areas in order to solve complex tasks. This type of organization may not be exclusive to decision-making tasks. This might extend to other cognitive processes such as language.
Secondly, through the use of graph theory, the researchers were able to identify changes in the degree hubs from resting states to IGT. More specifically, the DMN decreases in degree from rest to IGT, whereas the FPN increases in degree. This suggests that the FPN plays a more functional role in task demands such as IGT, whereas the DMN becomes less dominant compared to its activation in a rest state. This coincides with previous findings that the FPN plays a key role in the integration of information from other networks during a task state. The takeaway here is that the brain changes its network organization in response to the different task demands, and that the FPN may be an integral hub in this process, allowing for the integration of information. Lastly, this study is important in another way. Not only were changes in network organization an important finding, but the way in which some of the analyses were performed was new to the field of psychology. Graph theory, before this study, has been largely used in resting state fMRI scans. The researchers extended graph theoretical study to examine changes in network organization under decision-making. This new technique is relevant as it may now be a viable option for analysis for other researchers and could lead to many studies in the same vein.
However, did not come without its fair share of limitations. As mentioned earlier, the brain's network organization during rest was a more clustered and locally ordered topology, whereas during decision-making tasks such as IGT, it was a more diffuse and globally ordered topology. However, during IGT, it was noticed that local efficiency decreased, but these results were not free of threshold effects, so this is a tentative conclusion and should be therefore further investigated.
The researchers of the study hope that their findings and methods used will serve as inspiration for others to take on similar questions and studies. Using network analysis and graph theory, other tasks and cognitive processes could be examined and compared to resting state activation, such as memory, language, and listening, to name a few possibilities. As mentioned earlier, no association was found between network metrics and net advantageous selection, possibly due to sample size. For this reason, it might be wise to undertake a similar experiment, but using a larger sample in order to obtain more power. Got any eights?
No, go fish. Oh, hey, you're still here. I hope you enjoyed our presentation today, and I hope you learned something new.
And remember,